Hello, this is Xuhui, and I'm going to talk about distributionally robust Bayesian non-parametric predictions. This is a joint work with Jose, Yusuf, Viet, and Sven, and our work is supported by the Air Force Office of Scientific Research. The problem that we are tackling is to estimate a regression function non-parametrically. And typically, people use Gaussian models or Gaussian fields for convenience and for tractability purpose. However, the reality is not necessarily to be Gaussian, and so the user is inevitably misspecifying the model. And in particular, that includes misspecification on the covariance structure and the misspecification on the smoothness of the underlying regression function. And here we provide a robust framework for this Bayesian non-parametric regression estimation and Bayesian inverse problems. So first, let me describe the problem setup. Suppose we consider a compact domain with a smooth boundary in a d-dimensional Euclidean space. The input is a function b that we assume to be continuous. We also assume that there's a forward operator t, which is a boundary linear operator that transforming u to another function, transforming b to another function u. And the data or the measurements we consider are noisy observations of the value of the function u at some design points. And we denote the noise vector by epsilons. Given all these measurements, we can consider the problem of doing regression estimation on u, or we can do an inverse problem to recover sample path of b. And in this talk, I'll focus on the recovering the sample path of u. And the conventional objective is to consider a Bayesian L2 risk minimization problem. So the statistician is seeking for an optimal estimator that minimizes the Bayesian L2 risk, whereas the Bayesian model is a joint Gaussian model, which we denote by P0 over the prior input process on B and the noise vector on epsilons. To add a layer of robustness to this kind of problems, here we are following the distributionally robust optimization formulation. So we propose a min-max objective. And in this objective, we are assuming that there exists an adversary who can choose different models of P that depart from the user-specified P0. And in particular, the adversarial's chosen model P can be non-Gaussian. We further constrain that the adversary's chosen model P has to be within a delta distance to the user-specified P0. And we'll define the Wechsler distance in the next few slides. Here we remark that the Wechsler distance are added to ensure the non-parametric robustness. We can observe that here the decision variables are non-parametric predictors, and the adversarial's chosen set are infinite dimensional set of probability measures, and the probability itself are infinite dimensional processes. So here we are looking at a fully infinite dimensional game. And having proposed this problem formulation, there are a few natural questions. Does the game has a well-defined value in the sense of the min-max value equal to the value of the max-min? And is there a Nash equilibrium? Is it unique? How can we compute it? And what can we say about these structures? And in the remaining time, I'll be discussing the answers to these questions. But first, let me introduce further assumptions and configurations of our modeling framework. Here in our framework, we are considering quite general the Gaussian process priors given by this infinite series, which are a sequence of eigenvalues kappa n, a sequence of RLD univariate Gaussians Gn, and a sequence of orthogonal bases of L2D, which are the ENs. We assume the series converges in the sense of the continuous function space and as well as in the sense of L2. We also assume that the prior process is 4 rank, and that's equivalent to saying that the kappa n's are non-zero. As a canonical example, we can consider the Merton process priors, where the eigenvalues are induced by the Laplacian eigenvalues lambda m, and eigenfunctions are given by the Dirichlet Laplacian eigenfunctions. And in this prior assignment, the sequence kappa n, or equivalently the index alpha, controls the smoothness of the prior. As we discussed before, we assume that the adversary can add perturbations to the sample path. And here we make some assumptions on the space of perturbations. Our space of perturbation is quite general, that includes these Sobolev-type spaces. So these type of spaces are subspace of L2 space, and with a Hilbert norm given by a weighted L2 norm that puts different weights to different modes or different frequencies of the function. And here the weights can be viewed as penalizations to the perturbations for different frequencies. As a canonical example, we can parameterize the sequence of weights by the Laplacian eigenvalue raised to some power beta. And typically, the reproducing kernel Hilbert space of some Gaussian process will correspond exactly to this kind of perturbation, to these kinds of Sobolev-type spaces. As a recap, the goal of the statistician is to consider this min-max objective where the Washington distance is given by a cost function that's composed of the usual Euclidean L2 norm for the noise component and the Hilbert space norm for the function component. We also make some assumptions on the forward operator. Recall that U is equal to TB, where B is the prior input process, and we assume that T is a linear bounded operator from CD to space to CD space. And moreover, there exists some positive sequence W tilde, and along with a positive constant, such that the operator T is bounded when restricted to the space of H indexed by this and W tilde weights. And moreover, we assume a compatibility assumption that Wn tilde is of smaller order compared to the original Wn. So this intuitively they say that T is bounded even if the perturbations are made to be slightly rougher than the adversarial's real choice. Having introduced this problem setup, our first result is a strong duality result that says the value of the min-max game is equal to the value of the max-min game. And so this says the game has a well-defined value. And in this result, we use a general duality result that appears in Blanche and Murphy 2019 to characterize the linear worst-case distribution. Our second result says that there exists a unique pair of Nash equilibrium associated with this min-max game. Moreover, we show that this pair of Nash equilibrium can be viewed as limit of a sequence of finite dimensional approximations. And this moreover gives us an algorithm to practically compute an approximation for the infinite dimensional objects. Moreover, we show that the optimal predictor follows a linear prediction rule, and the worst case distribution follows a Gaussian measure. And the final dimensional version also appears in the paper of Nguyen et al. In 2021. Our framework in this paper applies quite general to canonical problems in Bayesian regression and Bayesian inverse problems. Particularly, that includes the example of Gaussian process regression, where the operator is the identity operator, and in the one-dimensional case, the Laplacian eigenvalue and eigenfunctions can be calculated easily. Other examples also include the Laplacian equation, the solution to the heat equation, And with some slight modifications, our framework also applies to Radon transform in the plane, which is a hot topic in computational tomography. And in the remaining time, I'll report some numerics, and I'll be mostly focusing on the one-dimensional Gaussian process regression example. We assume that we have 10 designs that's equispaced, either in the whole 0-1 interval, we call regular designs, or in the first half of the interval, which we call irregular designs. And our goal is to investigate the qualitative behavior of the worst case measure, as well as investigate the effect of hyperparameters involved. Particularly, that includes the smoothness assumption on the smoothness parameter alpha, the perturbation penalty parameter beta, the size of the Washer sample radius delta, and the noise level sigma. We follow the Frank-Wolfe algorithm developed in the paper of Shafi-Izadeh Abadi in 2018 to calculate the finite dimensional approximations to our Nash equilibriums. First, we look at the correlation functions for the regular design case. Particularly, we can look at the prior and posterior correlation functions for both the nominal and the worst case measure. We can see here that the worst case posterior particularly shows some ripples in the correlation structures. And similar phenomenon holds if we look at the irregular design case. We also see the ripples, and this indicates that the worst case measure is qualitatively different and structurally different from the nominal measure. Apart from looking at the correlation function, we can also look at the marginal variances, and here we look at the regular design case. If we compare the worst case posterior and the worst case prior to the nominal posterior and the nominal prior, we can see that the marginal variance got inflated. And particularly for the observed locations, the inflation is minute. And for the unobserved locations, the inflation is significant. So intuitively, this indicates that to guarantee robustness, the worst case measure induces greater uncertainty in regions where information is limited. And this kind of phenomenon can also be observed in the irregular design case. We can also compare the nominal and the worst case policy, and we can see they're qualitatively different. Finally, we look at the effect of hyperparameters. As we can observe from the sample path of the prior and posterior nominal and worst case distributions, we see that with a larger alpha value, meaning that our priors are smoother, the worst case tends to induce a sharper contrast between the observed and unobserved locations. And similarly, if we consider a smaller beta value, meaning that there's less penalty on the higher frequencies on the higher modes, the worst case tends to introduce a sharper contrast between the observed and unobserved locations. And similarly, if we consider a larger delta, meaning a larger versus more admissible perturbations in the Wasserstein ball, the worst case tends to induce a sharper contrast. And finally, if we're considering a smaller sigma, meaning the smaller noise level, then the majority of the penalty, majority of the transport cost can be allocated to the transportation of the function component. Then it also introduces a sharper contrast between the observed and unobserved locations. Lastly, to conclude, we propose a min-max distributionally robust regression formulation with infinite dimensional Gaussian prior measure, and we show that there's a computable Nash equilibrium. This suggests that Gaussian models are distributionally robust in a strong non-parametric sense in our framework when the Washington distance are defined by a suitable Hilbert space norm. And that's the all my talk, and thank you for your attention.